Okay, we can proceed, and if it is written on the table, let's start with these tasks. With the task 1, how do you understand this question? And formally speaking, I have not defined the Lie Subalgebra. How do you understand this, the question? Between one space is the Lie Subalgebra of another Lie Subalgebra. So SON is a subspace. I've defined it as a subspace of skew-symmetric matrices. SN is the A of SLN such that minus A.
So you need to prove it.
What does it mean that it is a Lie Subalgebra? For example, R3 with the vector product is a Lie algebra, and for example, we can embed it into GL3. Just here you have a vector x, y, z, and for example, we can concede the matrix like this. So this three-dimensional space is a subspace of this Lie algebra.
So I think.
But here it is not Lie Subalgebra.
Yeah, for I think we can create an element of SON and then see that the determinant gives 1. Then you can say that it's like a subspace.
No. Just what does it mean that one subspace is a subalgebra, Lie Subalgebra? Okay, it means that it is a Lie algebra with respect to the commutator here, with the same commutator, with the same algebraic structure. So if you consider this embedding, it is obviously an embedding of linear spaces, but the commutator of here doesn't correspond to the commutator of matrices of this type. You understand?
So you mean like the same commutation relation will be for SON and SLN?
So formally speaking, we have defined a homomorphism phi if J H is a homomorphism of Lie algebras if phi of x and y in G phi of x and phi y in H. Okay. G is a Lie Subalgebra of H if G subspace is subspace and the commutator in H, but if restricted to G, define a Lie subalgebra. A Lie algebra structure. A Lie algebra structure. So here
When you say restricted, what does it mean? It means
it is also a fact that it could be restricted. So if we take two objects from the subspace, the commutator in a bigger algebra is an element of the subspace. Okay? So we need to verify the following fact, that if hint, we have to verify that if A minus A and B is minus B, then the commutator minus AB. Could you verify this? Clear? Could we write it?
Write the definition of the commutator. So it's AB minus BA. Transpose it. Then we apply the transposition to this, and it's BT minus BT. Then we use these facts. So it's just BA minus AB, which is
Very good. Very simple, very good. Thank you very much. Done. Task 2. It is about the exponential of skew-symmetric matrices. We should verify that the result is the orthogonal matrix. And moreover, an orthogonal matrix with the determinant 1. Do you remember what is an exponential of a matrix? Yes. It's just the series of the exponential A, K, factorial. But we need to use some fact that if A and B commute, then exponential of A plus B is equal to exponential of A multiplied by exponential of B. First of all, do you know this fact? How to derive it?
obvious previous one, that if they commute, then they should be this.
Yes. If they don't commute, it's not right. That even very important calculation in quantum mechanics. But if they commute, we have this. Why? How to derive it?
Then you can try to exponentiate the matrix and check the right hand side equal to left hand side.
Yes, it's just a classical calculation. It's just for numbers. like for numbers, but for number it is known. So the calculation for commuting matrices is like the calculation for numbers. So if you know it's for numbers, it's true for every commuting elements. And for example, exponential of minus a is exponential of a minus 1. Okay? Because minus a commute with a, if they do this for b equal minus a, it is just 1. And so they are inverse to each other. Okay? I suppose that it is the only thing to demonstrate this. Please try to do it.
We already solved the second task?
Not yet, but it is the important part to solve the second task. Important fact to use. Uh-huh.
So we have to consider exponent of a and times the transpose of exponent of a.
Yeah.
And then we use the properties to show that it's...
Yes, it's not difficult, but could you write it once again? Please. You can erase what you want. It's the first task, yes, but why you can... Yes. Yeah. No.
I guess we can do it with the definition.
Yes.
Yeah.
Mm-hmm.
And so, and it can go on?
Is it clear, this first? That,
Okay.
so we can...
It should be like this, otherwise...
We just have to apply it term by term.
Very good.
Yeah. And then we use that it's an element of this algebra. That means that we can write this.
Mm-hmm.
Then
Yes.
then we use the multiplication rule. So it's just the identity matrix.
Very good.
So
Yeah.
it's an element of this algebra.
Yep. Thank you very much. But why is determinant is 1, not minus 1?
Which determinant?
The determinant of this exponential. So this fact is the fact that it's an element of the orthogonal group, but not special orthogonal. Generally, you can obtain the determinant plus or minus 1, but here it is only plus 1. Do you have an idea? So this S means that the determinant A is equal 1, not minus 1.
So,
How to work with such strange questions?
and you ask like why the determinant is 1 or what?
Yes, and it will be 1, not minus
Yeah, it
1.
will be 1, yes. Yes, it will be 1.
And if I remember well, the formula generalizing this exponential is called Campbell-Hausdorff formula, very used in quantum mechanical calculations.
Maybe for the determinant, we can use the property of the determinant of an exponent is an exponentially trace.
Yes. is 0 because it's skew-symmetric.
Yes.
It has 0 element on the diagonal. And how to, just to keep in mind this, why it's true.
We can use the
So you ask why e to the power determinant.
Yes, why this equality is true. Yeah.
we can use Jacobi decomposition.
Jacobi decomposition.
There's many steps to prove this, or maybe it can be done easier.
I prefer such an argument. It is obviously true for diagonalizable matrices. Okay. So it is true for diagonal matrices. Just because, so if A is 1 and n, then the exponential of A is just
And then just
the determinant of is the product of it is the exponential of the sum of lambda, and this is the exponential of the trace of A. Okay?
so for non-diagonal it will not work like that.
But generic matrix is diagonalizable. Okay? There is a basis in which it is diagonal. And you can work in this basis. So for a generic matrix, it is true like for a diagonal matrix. Okay? Because it is this equality, it doesn't depend on the basis. If you change the basis, it became the same quality. Okay, so you could verify it in a basis in which the matrix is diagonalizable. But there are matrices which couldn't be put in diagonal form. But you see, there's an equality. If you consider it as an equality on the space of matrices, it is satisfied almostly everywhere.
What is everybody?
At a generic point, so with probability 1.
Are there any examples of a matrix for which it's not true?
No. But it's a way to demonstrate that it is true for all matrices. If it is almost true on the space of matrices A, it is true for all matrices. Because it's a smooth function. Both sides of this equation are smooth functions. Okay, but it's a little bit cheating manner to think about it. But it is true, and in our task it produced a result. But now we return to the definition of our list of terms, to some aspects of groups. And we will work just with group S3, which is the group of automorphism of the set of 3 elements. So there is a set of 3 elements. And the automorphisms, I don't know how you denote them traditionally, but for example, 1, 2 denotes the cycle, the transposition changing two first elements and which stabilize the third element. So this transposition lies in the stabilizer of the element 3 if we consider this group acting on the space of on a set of 3 elements. First of all, we obviously have the unity element, the transposition 1, 3, the transposition 2, 3, and 2 cycles, 1, 2, 3, and 1, 3, 2. It means that 1 goes to 2, 2 goes to 3, and 3 goes to 1. And it is the rotation in the opposite sign, in the opposite sense. So this is the set of all elements of the group S3. And the important thing is to represent all elements in terms of some generators. Let us consider transposition 1, 2, and 2, 3 as generators. We can represent all other elements in terms of these generators. And moreover, there are some relations in these generators. You know them very well. 1, 2 square is 1. 2, 3 square is also 1. Then the composition of them 1, 2, 2, 3 means that firstly we apply these generators to our set. So it's better to represent it like this: 1, 2, 3, 2, 3, change these elements and stabilize 1, and then we apply 1, 2 like this.
Is this practice obvious to everybody that like the generator 1, 2 square is equal to the identity?
This one?
Yes.
It's transposition, so it doesn't remember how we transpose it.
That's why it's like unitary.
Yeah. So there is a very close object to the symmetric group, which is called the braid group. Like this one.
Yes.
In this one, it is not unit. But in the symmetric group, it is like this. So this composition, but you see, we apply such element to something on the right. So firstly, we apply this, then the left-hand side, the left component, and we obtain what is it in terms of all elements of our group. Where goes 1 through?
1 goes to 1?
Yes, to 2.
Yeah, 1 goes to 1 and then 2
Uh-huh.
goes.
So it is this cycle. Okay.
Yes.
Another product. It is the product on the opposite, in the opposite sense. So you see, we have taken 2 elements and we try to give all the products, and we just compose the monomials. The powers are trivial, so there is no sense to consider higher powers of each generator. But there are mutual monomials, the product like this and the product like this. So if we take the same notation, first of all we get transposition of 1 and 2, which stabilize the element 3, and then 2, 3 exchanges 2 and 3, And this is the second cycle, the full cycle. What is important in this? Okay, and there is another. There is an element of the power 3 in this group in terms of this set of generators. Let us take. Let us take such a. Okay. The monomials of power 3. So if you multiply this monomial by 2, 3, it gets the element 1, 2, due to the involutivity of each element. So the only way to compose something of the power 3 is this product. Okay? What do you think about it? What is it as an element of the symmetric group?
What the question again? Is it?
We know all elements of the symmetric group.
Yes.
And now we represent them in terms of generators. They think that two such generators is sufficient set of generators to produce all elements of the symmetric group.
Yes.
We have composed the element of the highest length in this group of the element of the length 3. What is this element in this list?
1, 3.
Yeah. And another element in this list, another monomial of order 3 could be obtained if you multiply this by 2, 3 on the right. First, I'm sorry.
Oh, why it's not 3?
This is, I started by 2, 3. Okay? So it's mistake. And now I will write this.
It's like 1, 3 here in the previous case. And here, 1 goes to 1, no, 1 goes to 3, and 3 goes to 1, and 2 goes to 2.
Yes. And it is a very important relation in the framework of our course. It is called the Yang-Baxter Equation. It will be written in a quite another form, but it's the same. Let's keep it else in mind. It's the Yang-Baxter Equation.
So, did I understand correctly? Yeah, did I understand correctly? Why this is 1, 3?
1, 3, because 1 goes to 3, 3 goes to 1, and 2
Goes to 2.
is stabilized.
But the same is here also.
Yes,
So both are the same thing.
yes. Two such elements represent the same element of the symmetric group, but in two different ways.
Yes.
And the fact that the different ways represent the same element is known in quantum integrable systems as the Yang-Baxter Equation. We will discuss it in the part of our course called the R matrix technique. Let G be a finite group then C of G is a group a group algebra. It means that it's the set of linear combinations of elements of the group. G is the set of linear combinations G. And multiplication of A, G So you see, G is a finite group, so we consider just the linear space, the vector space, with generators which are element of the group. Okay?
And A is a complex number.
Yes, A is a complex number, so which is indexed by an element of the group. Okay? So it means that we should consider in this case, in the case of S3, just some element A, E multiplied by E plus A1, 2 multiplied by 1, 2 plus A1, 3 multiplied by 1, 3 A2, 3 2, 3 plus A1, 2, 3 1, 2, 3 A1, 3, 2 multiplied by 1, 3, 2. And we can multiply an expression of such kind. Okay? How we multiply? Term by term, and we use the relation in the group. So when we multiply this element by this element, we know that this by this is this. Okay? And then we make together the terms with the same generators. So we obtain again an expression of the same type. Okay? So starting with each finite group, we can construct an associative algebra, which is called the group algebra. Okay? So the center of an associative algebra, you know, I suppose you know what is the center.
So again, the definition of associative algebra is this, right?
Yes, yes. Your home task 3, home, to describe the center of the group algebra of S3. The center of the group algebra. You know what is the center? The set of elements which commute with all elements. Okay. So you see, it's identity is always in the center, but there are some non-trivial elements in this case. and which will be related to the conception of integrability in what follows.
We haven't started integrability yet. Okay.
Yes, it's the first step. This task is the first step to think about the integrability. But it is your task for homework, and now we will discuss the representations. Remember that our statement was statement S3 SO2 is a representation of S3 in R2. Let us discuss the statement and discuss all unclear parts of the statement. What to demonstrate, what to do. Representation means a linear representation. You remember?
We haven't formally defined what is representation.
Sorry?
We didn't formally define what is a representation.
No. I have given you a definition. It is a homomorphism to the group of linear transformations. But here it is a subgroup of GL2. So we have to demonstrate that this embedding is a homomorphism of groups. That the product here goes to the product then there. Let's think just a few minutes of how to work with.
So we need to check it, right?
Yes, but firstly you have to write down what to check. And for the Yang-Baxter equation, you see that it is true even in the braid group, even if you don't add the involutivity condition. If you don't suggest the involutivity condition. And it's a different story, but it's one of the miracles of modern mathematical physics that some quantum integrable models produce invariance of knots. It's a topological problem to find invariance of knots. Knots. Okay. You know what is a knots? Well, links and knots. It's a yes. So it's a how it is called trefoil knot. How one calls this this non-trivial knot? It's the first. It's a most simple non-trivial knot, and there are a lot of different knots. And this simple topological problem produced many applications in other subjects. For example, in topological quantum field theory, in Chern-Simons theory, the Wilson loop produced the invariance of knots, the Jones polynomial of knots. And some reasons for this are in this very basic structure of the braid group and of the Yang-Baxter equation, which is just a linear representation of the braid group, in a sense. Okay, but we are working now in this context, so I don't know, maybe it's better to write it in coordinates, so you know now the generators of this group. 1, 2, 1, 3, 2, 3. I'd like to write it 1. It's one cycle, the inverse cycle, and this is also transposition, but in terms of these two chosen transposition, it's an element of length 3. So these are all elements of S3. Maybe it's better to just write down what are the matrices of these elements. Do you remember my definition how to construct? So we choose 3 roots of unity on the unit circle. 1, 0, minus 1, 2, minus 1, 2, and minus square root of 3 over 2. And 1, 2, let this be 1, 2. This is the point 1, this is the point 2, this is the point 3. And now we construct isometries which act on this triangle by the element of the symmetric group on its vertices. Okay? So for example, 1, 2 is the it's the symmetry by this axis, with this axis. It's a symmetry transformation with such an axis. I don't know. Maybe it's better to write down the matrices of these transformations to understand that the multiplication of matrices is the same as the multiplication of elements of the symmetry group.
So how can I represent in matrix?
The symmetry transformation?
Well, the 2, 3.
Yes, it's better. Yes.
But the 1, 2 is not that trivial.
Not trivial, but not too very simple,
Yeah.
not very complicated. Okay?
How do you get it?
I see the images of the basic vectors. Always the columns of the matrix of the linear transform are the images of the basis vectors. This is the image of the basis E1. It is stabilized by, this vector is stabilized by this symmetry transformation. But the vector E2 changes the direction if you make this symmetry transformation. Okay? But 1, 2 is a little bit more complicated, but not so much. So what's the image of this vector? Yes.
So the column is
yes. In the second column.
Opposite, but it will be like 3 over 2, 3 over 2.
We can see this one. So it is like this, but what are the coordinates?
One half or
No,
square root
1/2 is here.
Yes, and up is the square root of 3 over
Yeah.
2.
What's the image of this element? 1, 3. But by definition, we have. This is just a question to compare the product of matrices and the product of generators. So does this transformation, this transposition. But I'd like you write it yourself, and then we compare.
So the first will be like minus 1 over 2 and minus root 3 over 2.
Minus.
Minus 1 over 2 and minus root 3 over 2.
Okay.
And the second row will be yes, maybe.
The column.
Yeah,
Uh-huh.
column, yes.
Uh-huh.
So it's like 3 over root 3 over 2 and
Minus.
minus 1 over 2. Yes.
Okay. We can try to verify that this is one. Both of this product is equal to this one. Would you like to?
By matrix multiplication.
Yes. It's a part of the homomorphism property. If the matrices like this satisfy the same relation, it's a part of the homomorphism property for this map from the symmetric group to the group of matrices.
But
Did you succeed?
here in the first matrix the trace is 0, but in the last one trace is like minus 1.
Okay.
It's okay, right?
The trace of the product of matrices is not a good invariant. You know, the trace of product is not. No. You see that the trace of A minus 1 B, A is equal to the trace of B. But here A is not.
No, I'm saying in like the first two matrix the trace is 0, but the last matrix trace is minus 1.
I'm not sure that it is right, because you see, so 1, 2 is equal to 1, 2 minus 1. So I think that it is not right.
It's not right.
I think so.
Then should be like plus 1, I guess.
It should be plus.
Yes. No, it's okay.
So in our case, A minus 1 is equal to A. So what we get in this relation is the conjugation. And conjugation doesn't change the trace.
Is the last column correct? For 1, 3.
Like this. Here is minus, and here is plus. You see the second vector is transformed to this one.
Yes.
Minus, plus.
first one?
This one? It's the positive rotation, the case to 2p over 3, 2 pi over 3.
Yeah, yes, yes.
So the first vector goes to this one. The first basis vector goes to this one. Okay. And the second goes to this one. It is not of trace 0, but it's okay. And 1, 3, 2 is the rotation in the opposite direction. If you remember that the rotation is always this matrix of this type. Okay. So you should change the signs in the off-diagonal part of the off-diagonal part. So now you have all matrices, maybe even simpler to multiply pair of these matrices to obtain this one. You remember that 1, 2, 2, 3, 3 to 1, 3 to 1. It is equal to 1 to 3 in the symmetric group. Okay, and 2, 3, 1, 2 is equal to 1 to 1, 3, 2. Else it's an equation in the symmetric group. So we have to verify the same relation in the matrices. And this will verify that our map is a homomorphism. So maybe it is simpler. So you need to verify to multiply only two matrices here.
Check it's equal to that.
Yeah. And matrix 2, 3 is very simple. So multiplication of this matrix on the right and on the left is just the multiplication of rows and columns by the diagonal elements. So you can see. It's correct? Uh-huh. Okay. So maybe now you can verify this? Yeah. Okay. But it is doable.
Yes,
Doable. just some minutes to do. So you know how to proceed, and I'd like you do it at home. And I want to propose some another way to think about it. So you see, we have our group S3. We have a group of isometries of a triangle. It means that it is a subgroup of SO2, which is a subgroup of GL2. This is a subgroup of SO2, which preserve a triangle. Okay? Preserve a triangle. So it transforms the triangle into the same triangle. All points of this triangle goes to the points of this triangle. Okay? Now, if you have an element here, A, here, it's an element here, here, and here. We can restrict it to the set of the vertices of the triangle. Vertices of. So we transform all points of the triangle to the points of the triangle. but the vertices are transformed into vertices. Okay? And the vertices of a triangle, it's the set of 3 elements. So the restriction of an isometry of a triangle to the set of vertices, it's an element of S3.
It's the same thing.
This restriction, it is just an element of S3. Okay? S3. Because the set of vertices is a set of 3 elements, and this isometry of a triangle acts on its vertices as an automorphism of the set of 3 elements. Okay? But I'd like to say that this restriction is a homomorphism.
With what?
You see, an element of the isometry. I have here a map from the group of isometries of a triangle to S3. Just restricting this isometry to the set of vertices. And this restriction is a homomorphism. Because if you make a composition of 2 isometries, it produces a composition of maps on vertices. Okay? This map is a homomorphism. And now we have to say that it is a bijection. Because if you know the image of vertices of a triangle, you know all the isometry. Because the images of the vertices of triangle define all the isometry. Isometry preserves the distances. If you have 3 points and you know the images of these three points, you know the image of all points because it is defined by the distances from the 3 initial points. It should 1, 2, 3. 1, 2, 3. It should be here. No other chances. So it means that an isometry is defined by the images of the vertices of the right triangle. Okay. So it means that it is a bijection. It is a homomorphism and a bijection. And obviously it is the inverse of this inclusion, this embedding. Okay. But it is always good to make calculation in matrices. It is very sure. Okay. The next part of our tasks is related with the notion of an action, of stabilizers, of orbits. Okay? And the first task will be the following. Stabilizer. Let us consider SO2 action on R2. It's just conventional notation for the action of the group on the set. SO2 a group acts on R2 just by isometries. And our task is to define orbits, stabilizers of different elements, and to say if it's free, transitive. Okay, so the first part is to define the orbits of element through this action.
Homework, or will you do here?
Sorry?
Is it
Here,
homework?
here, we have time.
For a point on the plane.
On the plane, yes. R2, the group. Is it clear that this group acts on the set? So, in a sense, it's obvious because so SO2 is the subgroup of GL2R, which is the group of all linear bijections, linear transformations of R2.
So the orbit of a point is a circle whose center is the origin.
Yes, yes, that's right. But could we comment it? So that's right. So the orbits are the circles, and even the degenerate circle, the point.
So this is the orbit of this action.
Yeah,
So it's just a circle.
circles.
And the center is the center of the circle.
The center is also an orbit, but orbit of this element is this circle. How to demonstrate it?
How to demonstrate?
It's a fact.
So, yeah, we were discussing it. Prove or show something.
We have to prove.
So you can move with the definition of orbits.
And you see the orbits are different. So the orbit of the center is different. The dimension of this variety is different. So it's zero-dimensional, and all other orbits are one-dimensional. And the group SO2, how there are dimensions? How many independent parameters? No, one. Just one, just the rotation of symmetries, but the symmetries are defined by the angle of the axis. There are two connected components. No, in SO2 there are only one connected component, it is a circle. There are only rotations. So I suppose that it was a mistake. It was a representation in O2 before. S3 it was represented in O2. The transposition were the transformation with the determinant -1. Okay, but here there is SO2. It acts on R2 by rotations. So the dimension of the group is 1. The generic orbit is one-dimensional. But there is a very particular orbit which is zero-dimensional. And we have to compare it with the dimension of the stabilizer of the point.
Stabilizer for which point?
For the point from different orbits. So this is a generic orbit, and the point on a generic orbit. What is its stabilizer?
Only the unity.
Only unity. Okay. This point, stabilizer of this point, is the unit element. And 0 is very particular. Yeah. Yes. State of 0 is SO2. There is also an identification of the group, the quotient of the group by the stabilizer. Okay? It's quite evident. And we see here that here the group is S1 and the stabilizer is S1. And that's why the orbit is just a point. And at the generic point, the group is S1, but the stabilizer is trivial. That's why the quotient group is the same as the initial group. It is the circle, and the generic orbit is a circle. Okay? Let's see another examples of action. Second. There is an action of GL R acts on R2, GL2R on R2. What are the orbits, stabilizers? Is it free, transitive, or whatever? Yeah, that's right. So the orbits are 0 and R2 except 0. These are only two orbits on this section, but we need some comments, some explanations. Yeah. Are there some stabilizers?
So you're saying that this is the orbit of GL, this group acting on the plane?
You see all the space, all the set X with the action. It can be represented as a disjoint union of orbits. And
all this what represent?
yes, it's disjoint union of orbits, some elements, because orbits are not intersecting.
Okay, yes.
You understand that here the orbit of this element is equal to the orbit of this element.
Same.
But these orbits are not intersecting.
Yes.
And that's why all the set is a disjoint union of different orbits.
Mm-hmm.
It is very useful in many different contexts. So here, all the plane can be represented as the disjoint union of two orbits, just two orbits, just 0 and all except 0. So the statement that the plane except 0 is an orbit. Between 2 points which are not 0, we could find an element of GL2 which transforms the first point to the second point. So on this set R2 except 0, the action is transitive. We should demonstrate it, comment, so to prove this fact.
To prove the fact that
Yes.
this is transitive.
Yes, on this subset, so it's an orbit, and to find stabilizers. Because you see, this is a two-dimensional set, but GLN, GL2R is four-dimensional. So
So the stabilizer will be
two-dimensional.
yes. Stabilizer will stabilize the
Point.
points, yes.
Mm-hmm.
So if I have a plane
Mm-hmm.
without the origin, at which point will stabilize it?
This point.
Yeah, so for example, you have this point,
Mhm.
at which point will stabilize this opposite? I mean, 6
No.
point you said last time there.
No. Now we consider all the general linear group, all the group of linear transformations, not only isometries.
Okay, so now we have a point on a plane.
Yeah.
And what a stabilizer? Stabilizer is the point which stabilizes.
But here it depends on the group you consider. In this group, the stabilizer is bigger
Okay.
than in the group of orthogonal matrices.
So we should find some other points which will stabilize it.
No, you have to find transformations
But
which
how-
stabilize this point.
Well, reflection.
Reflection, it's an orthogonal transformation.
Okay.
Just general linear transformation. So matrices of this type, invertible matrices of such a type. And this is the point, xy. How to describe matrices which stabilize this point?
We have to impose some conditions on the
Two conditions.
matrix.
Yeah.
So what are the conditions that we need to impose?
For example,
Well, we can.
You can rotate the plane by the full rotation from it again, it will be the same point, isn't it?
it is not an element of GL2R
Yeah, that's
because it should preserve zero.
So we can write down that any times the column of x and y equals to x and y.
Yeah.
Then find this thing.
Yes, but we need to describe. It's not the one matrix. Non-unitary, yes, but there is two-dimensional space of matrices of such type, and it is a subgroup.
But identity will always be this.
Identity obviously lies in this subgroup. And if xy is a 0 point, it's the whole group. You see? But if it is not a 0 point, it's a two-dimensional subgroup. How to... So, first statement, A, that the orbit are like this. It's a statement. So for each 2 points which are not 0, there is a linear transformation which takes the first point to the second point. It's a first statement. B. Stabilizer of 0 is the whole GL2R. And for each point of the second orbit. So this is the two-dimensional variety. So it's something which is described by two equations, but two independent equations. So you see, if you write down this one, this matrix equation, it is not evident that they are independent. So for example, for 0, it is not two-dimensional. It defines the four-dimensional subspace, subvariety. So you can work with this definition a little bit. Let us finish by discussion of the first step. Could you say why the orbits are like this? So the statement here that in this action there are only two orbits, one point orbit and all except this point 0. It means that for 2 points from this subset, there is an element of the group which transforms the first point to the second point.
What do we need to prove? That these
It's a statement.
Yeah, and so we need to prove that there are only two orbits like these.
Mm-hmm.
So we can consider 0, for example.
It's okay.
And if we act on 0, we only get 0. So it's
That's fine. Yes.
And if we consider another point,
Uh-huh.
we can always translate, not translate it, but to get another point.
Yes, yes. It is written. It is written in this that it is only one orbit. There are no separation in different types.
Just because we have one
Yes.
plane, right?
It is not evident. It's true, but we have to demonstrate it.
So it's like proof that why the second condition is.
Yeah, yeah. So for each 2 points, which are non-zero, we can find a linear transformation which brings the first point to the second one.
So maybe we can take the following. We can take some two elements P and Q as like some points, or the column, and then take some, as an example, A from a matrix, and then act on the matrix and get the second point. Just like an example, not a proof, but an example. It could be possible.
Maybe, but
But do it.
yes, try to do it. So, for example, if you try to find the orthogonal matrix, you can't,
Why?
because orthogonal transformation preserves the distance. So the whole plane, it is separated in a variety of orbits. But
But you can take a general linear matrix.
it is not evident. It's a point of proof. So the statement is written here, but we need a demonstration.
So let's first think about A from matrix on.
Mm-hmm.
So maybe we can just present a matrix, or
As you like.
so we can write down an equation, for example, and just fix the points, and then base.
All means are good. What you want. But we need a strong demonstration, mathematical demonstration of this fact. I don't remember the number, but it is also for the homework to describe the action, the joint action of GL2R C on itself. On itself. It means that an element G from the group acts on an element H, but on the group consider it as a set. G from the group acts on H from the set as G minus 1 HG. You understand that GL2 can act on itself by conjugations. It is called the joint action of the group on itself, and there is the same question. What are the orbits? What are the stabilizers? How the set of all matrices is separated into the disjoint union?
I didn't understand that.
Mm-hmm.
Can you repeat it shortly?
Yeah. The task is to describe the joint action of the group JL2C on itself. The joint action of the group on itself is defined by this formula. So this is the element of the group. This is the element of the set. But in this case, they coincide. They play different roles. So this element of the group acts on H as an element of the set, and it acts by conjugation. So first of all, I suppose you have to understood that it is an action. So it acts. So it is some transformation of the space, and it acts as automorphism of the space. And first of all, you need to understand that it is an action, and after this, the question is to describe how the group J2C is presented as a disjoint union of orbits. What are the orbits? What are the stabilizers of elements in different orbits? There are different orbits of different dimension in this space. But this question, I suppose it will be it will stay also as a task for homework. Okay, we finish. Thank you very much.